Hi, welcome back to the channel. Vehicle braking systems represent the most fundamental safety component in automotive design, serving as the last line of defense in preventing collisions. Over the decades, brake safety regulations have undergone significant transformations to address evolving vehicle technologies, increased performance capabilities, and shifting consumer expectations. Most recently, the regulatory landscape has dramatically shifted to accommodate the unique challenges presented by electric vehicles, driver assistance systems, and autonomous driving technologies. These latest regulations represent not merely incremental improvements, but a fundamental reimagining of how we evaluate braking performance in an increasingly complex automotive ecosystem. Brake safety standards began with basic performance requirements established in the 1960s and 1970s when the NHTSA first introduced Federal Motor Vehicle Safety Standard 105, or FMVSS for short, for hydraulic brake systems, followed by FMVS of 135 in the 1990s. Similarly, the United Nations Economic Commission for Europe established Regulation 13 as the foundation for European standards. These early regulations primarily focused on stopping distance, brake fade resistance, and parking brake effectiveness for conventional internal combustion vehicles. The testing methodologies remained relatively unchanged until the 2010s, when the rapid emergence of alternative propulsion systems and electronic control modules necessitated a regulatory overhaul. The 2023 to 2024 regulatory updates represent the most comprehensive revision to brake testing protocols in over 2 decades, with several paradigm shifts. Perhaps the most significant change is the establishment of dedicated testing protocols for regenerative braking systems. The latest standards now require state-of-charge testing across multiple battery levels, 100%, 50%, and 15%, to evaluate braking consistency, transition testing between regenerative and friction braking systems to ensure seamless operation, fail-safe validation to confirm hydraulic system engagement when regenerative capacity is compromised, and energy recovery efficiency measurement as part of the overall braking performance evaluation. The updated regulations have substantially expanded requirements for electronic stability control integration with braking systems. This includes mandatory performance testing of brake-based torque vectoring systems, comprehensive evaluation of brake-by-wire systems under multiple failure mode scenarios, expanded testing of anti-lock braking systems on variable friction surfaces, and new protocols for evaluating stability during split and braking conditions when wheels encounter different traction levels. For the first time, regulatory frameworks have integrated autonomous emergency braking performance as a core component of brake safety compliance. This encompasses testing of sensor fusion systems that combine camera, radar, and LiDAR inputs, performance evaluation across varying lighting conditions, and adverse weather scenarios, validation of pedestrian and cyclist detection capabilities linked to braking activation, and assessment of false positive minimization to prevent unnecessary emergency braking. While significant strides have been made toward regulatory harmonization, notable differences persist across major markets. In North America, the NHTSA has emphasized performance-based outcomes rather than prescriptive methodologies, allowing manufacturers flexibility in achieving required stopping distances. The latest amendments to FMVS of 135 establish more stringent stopping distance requirements while remaining technology neutral. The European Union, through Euro NCAP, and the updated UNECE Regulation 13H, has taken a more prescriptive approach, detailing specific testing methodologies for each vehicle classification. The EU regulations place greater emphasis on pedestrian safety and urban environment braking performance. Asian markets, particularly China and Japan, have adopted hybrid regulatory approaches, with Japan's updated JNCAP protocols focusing heavily on elderly pedestrian protection and China's GB standards emphasizing high-speed stability during braking events. The updated regulations have necessitated advanced testing equipment and methodologies. High-precision GPS-integrated deceleration measurement systems have replaced traditional fifth-wheel testing apparatus, while robotic driving systems now execute brake tests to eliminate human variability. Thermal imaging cameras monitor brake temperature throughout testing sequences. Environmental chambers simulate extreme temperature conditions from -40 degrees Celsius to +50 degrees Celsius, and advanced data acquisition systems capture up to 1,000 data points per second during test procedures. These regulatory changes present significant challenges and opportunities for manufacturers. Development cycles must now incorporate extensive brake system validation across multiple propulsion modes, and engineering teams must optimize regenerative braking algorithms to balance efficiency and traditional braking feel. Compliance timelines have been staggered, with full implementation required by 2026 for most vehicle categories. Testing costs have increased by an estimated 15 to 30%, particularly for vehicles with autonomous capabilities, and design integration between propulsion, braking, and stability systems must be addressed earlier in development. For vehicle owners and the general public, these regulatory advancements translate to tangible safety improvements. These include more consistent braking performance regardless of battery state or environmental conditions, enhanced stability during emergency maneuvers, particularly on variable friction surfaces, reduced stopping distances across all vehicle categories with passenger vehicles, seeing improvements of approximately 5 to 8%, more intuitive brake pedal feel when transitioning between regenerative and friction braking, and increased reliability of autonomous emergency braking, particularly in protecting vulnerable road users. Looking ahead, brake safety regulations will likely continue evolving along several trajectories. The integration of artificial intelligence in braking systems will necessitate new testing protocols for machine learning algorithms that adapt to driver behavior. Additionally, vehicle-to-vehicle communication will enable coordinated braking among multiple vehicles, requiring new standardized testing for these cooperative systems. As fully autonomous vehicles become more prevalent, brake regulations will increasingly shift focus from driver-initiated braking to system-initiated braking under various operational conditions. This will require fundamentally new approaches to validation and compliance testing. The latest brake test safety regulations represent a critical evolution in our approach to vehicle safety, acknowledging the transformative changes in propulsion systems and autonomous capabilities. While presenting technical challenges for manufacturers, these updated standards ultimately deliver significant safety benefits for consumers while establishing a flexible framework that can accommodate continued technological innovation. As automotive technology continues its rapid advancement, brake safety regulations will remain at the forefront of ensuring these complex systems perform reliably under all conditions, serving as the ultimate safety net for increasingly sophisticated vehicles. If you like this video, give it a thumbs up, share, and also subscribe to this channel for more informative videos.